This wall is 45 feet thick at the top and 660 feet thick at the bottom, nearly 15 times thicker at the base than at the crest, and the obvious explanation is wrong. It is not thicker at the bottom to carry the weight of the concrete above it. It is not thicker because Lake Mead is enormous. You could drain 9/10 of that lake away, and this wall would not change by a single inch. Almost everything most people assume about why Hoover Dam is shaped like this is wrong. And the real reason is a rule about water that decides the shape of every dam on Earth. In the next 10 minutes, you are going to understand 3 things: why that wall has exactly that shape, where the electricity actually comes from step by step, from the reservoir to the transmission line, and the failure that engineers genuinely fear here, which is not flooding and is not cracking. And one more thing before we start. Keep the year 1941 in your head. Something happened inside this dam in 1941, and it comes back at the end of this video. It is the reason a different dam nearly destroyed itself 42 years later. Start with something much smaller than a dam. 2 containers, a tall thin tube, and a wide flat pan. Fill both to a depth of 6 inches. The pan holds far more water, 10 times more, maybe 50 times more, depending on how wide you make it. Now measure the pressure at the bottom of each one. They are identical. This is the part that surprises people. The pressure at the bottom of still water does not depend on how much water there is. It depends only on how deep it is. Here is why. Pressure at any point comes from the weight of the column of water directly above that point, and nothing else. 1 square inch at the bottom of the tube is carrying a 6-inch tall column. 1 square inch at the bottom of the pan is carrying exactly the same 6-inch column. All the extra water in the pan is sitting over its own square inches. It is not stacked on top of yours. And water pushes sideways just as hard as it pushes down. So at every depth, the water in a reservoir is shoving outward against the dam with a force set entirely by how far below the surface it is. At the surface, that force is 0. 10 feet down, it is about 4 pounds on every square inch. 100 feet down, 43 pounds. And at the base of Hoover Dam, the Bureau of Reclamation gives the maximum water pressure as 45,000 pounds per square foot. Divide that by 144 square inches, and you get 312 pounds on every single square inch. That is roughly the pressure inside a fire hose, applied to every square inch of a wall as long as 4 football fields. So the wall gets thicker going down because the push gets harder going down. Pressure rises with depth, so the structure has to grow stronger toward the base. Its final shape also carries the weight of the concrete itself and transfers the water load out into the foundation and the canyon walls, and that is why the size of the lake is irrelevant. Lake Mead stretches back over 100 miles, but the dam does not feel the lake. It feels the depth. Now follow the water because none of it goes over the top. It enters through 4 intake towers standing out in the reservoir. Trash racks screen out debris. Gates below control how much gets in. From there, it drops into a penstock, a steel pipe buried in the canyon wall, large enough to drive a truck through. And as the water falls, something specific happens to it. It trades height for speed. At the top, it is barely moving, but it is high up. At the bottom, it is hundreds of feet lower and moving fast. The height it started with has become pressure and motion. Friction takes a small share on the way down. At the bottom, the pipe curves into a spiral casing that wraps around the turbine like a snail shell, narrowing as it goes. That taper is deliberate. It keeps the water speed constant the whole way around, so every part of the turbine gets an even push. Inside sits a Francis turbine, curved blades on a vertical shaft. The water comes in at the rim, moving sideways and inward, and leaves at the center moving downward. And this is where people get it wrong. The turbine is not a water wheel being hit by a jet. The water turns a corner inside it, and it is the pressure on the blades together with the change in the water's angular momentum that drives the run around. That shaft runs straight up into a generator, where an electromagnet spins inside a ring of copper coils, and current appears. There are 17 of these machines at Hoover Dam. The output goes into transformers that raise the voltage, then out to the switchyard and onto the transmission lines, and the water simply carries on down the Colorado River, having lost almost nothing except its height. The 17 main generators come to 2,074 megawatts of nameplate capacity, and 2 small station service units round the plant total to about 2,080. From 1947 through 2008, Hoover averaged about 4.2 billion kilowatt-hours a year, though annual output moves with the water. With no fuel, there is nothing to burn. The sun lifted that water out of the ocean, and gravity brought it back down through a canyon in Nevada. Though the building of it produced one problem I still find slightly absurd. Concrete gives off heat as it cures, a small amount in a small pour. But this is 3.25 million cubic yards of it. Poured as one mass, the middle would have taken something like a century to cool, and it would have cracked itself apart doing it. So they poured it in separate blocks, and they ran pipe through every one. 582 miles of steel pipe buried in the concrete, with refrigerated water pumped through it to pull the heat out of the middle. That pipe is still in there. It was grouted up and abandoned in place once the concrete had cooled, and it is part of the dam now. Now the thing that actually keeps engineers awake. Inside that penstock is a column of water weighing thousands of tons, moving fast. Suppose you need to shut the turbine down, so you start closing the gate. Water compresses only very slightly, and it will not stop instantly. When the front of that column meets a closing gate, it piles into itself. The water behind it keeps arriving. All of that motion has to go somewhere, and it becomes pressure. This is called water hammer, and you have heard a small version of it. When a washing machine shuts its valve and the pipes in your wall bang, that is water hammer in a pipe half an inch across. Now scale it up. Close the gate instantly, and the pressure spike is not a few percent above normal. It is a large multiple of it, enough to split steel pipe and tear it out of the rock. So the gates are closed slowly, deliberately, unhurriedly, slowly. That is not caution. It is a hard engineering requirement. But there is a second enemy, and it is quieter. As water accelerates around a turbine blade or through a spillway bend, its pressure can drop so low that it boils at ordinary temperature. Not from heat, from lack of pressure. Tiny vapor bubbles form, travel a short distance into a higher pressure region, and collapse. Each collapse is microscopic, but it happens millions of times, and each one hammers the metal or concrete surface at enormous local intensity. This is cavitation, and over time, bubbles eat steel. Which brings us back to 1941. That year, for the first time, Hoover Dam had to run its Arizona spillway hard. Water went through the tunnel at very high speed, around a bend. When they went in afterwards and looked, they found the concrete lining had been torn open. The hole was 115 feet long, 30 feet wide, and 45 feet deep at its worst point. Not cracked, excavated, by bubbles. The Bureau of Reclamation documented it thoroughly, and then they fixed it the only way anyone knew how in 1941. They realigned the tunnel floor and they polished it smooth, which treats the surface. It does not touch the cause. The following year they tried something cleverer. They tested pushing air into the flow at Hoover, on the theory that air in the water would stop the bubbles forming. It did not work. The test was abandoned. And that is where this sits for a very long time. They have seen the damage, they have measured it, they have written it up. They do not yet know how to stop it. It takes 26 more years. The first tunnel spillway aerator that actually works anywhere in the Bureau's system is built at Yellowtail Dam in 1967. Now hold that date against this one. Glen Canyon Dam was finished in 1964, 3 years before the solution existed. So when engineers inspected Glen Canyon spillways and found early cavitation damage, they recommended aerators, and construction was scheduled to begin in 1984. In June of 1983, a record runoff forced Glen Canyon to run both spillways continuously for days. Operators reported the dam shaking and heard sounds from inside the tunnels. When the water finally dropped and engineers went in, they found cavitation had torn the tunnel apart from the inside. The fix had already been approved. The water arrived about a year before the contractors did. And Hoover itself, the dam where this all started, it did not get its own aerators until 1987, 46 years after its spillway was destroyed, 3 years after Glen Canyon, and there is one more number here worth knowing. Hoover produces about 2,000 megawatts at full pool, but the power a dam makes depends on the depth of water above the turbines, and Lake Mead has been falling for years. There is an elevation called minimum power pool at 950 feet. If the lake drops to that line, Hoover's 17 turbines can produce roughly 117 megawatts. Not half, not a quarter. About 6% of what it makes today. The dam does not stop working gradually. It falls off a cliff. So, look at that wall one more time. 45 feet at the top, 660 at the bottom. And every foot of that thickness is answering one number, which is not the size of the lake and not the weight of the concrete. It is depth. 590 feet of water, 312 pounds pushing on every square inch, and a wall shaped exactly to meet it. It is not a wall holding back a lake. It is a wall holding back a depth. If you take one thing from this, take the gap. Not a gap between knowing and acting, which is the story I expected to find. A gap between seeing something and understanding it well enough to stop it. 26 years for a phenomenon they could photograph the damage from on day one. Next time we look at where all of this electricity is actually going, because something is being built right now in Virginia that will draw more power than this entire dam produces. Not a city, one building,